In this video, I'm going to teach you guys how to determine, using our Discovery Viewer Pro software, what the energy level is of an individual substrate and of an enzyme, and then of the substrate-enzyme complex together. I'll then explain to you how to use that to determine the delta E overall. So first things first, as I delineated in the previous video, you want to begin by opening your Discovery Viewer Pro software. Next thing we'll want to do is hit the open icon and then open the file right here that has this title. This is a modified file that Dr. Harris has made of the neuraminidase Tamiflu complex. And for students who take this class from me, I'll provide access to a copy of this to you through Canvas. Go ahead and hit open. This is the enzyme Tamiflu complex. Tamiflu, by the way, is also known generically as oseltamivir. If you hit the rotation tool up here and rotate it, you'll notice that the enzyme, which is kind of big, looks sort of like a half of a sphere. The reason is once again because this is not the actual true full enzyme. It is a modified model of the enzyme that Dr. Harris has sort of scaled down. The reason is because the periphery of the enzyme, as it turns out, does not undergo any conformational changes that are significant when the substrate docks in its active site. What we're going to do now is rotate around this thing and see if we can determine where the actual Tamiflu, also known as oseltamivir, molecule is. You'll notice that there's this +1 number down there. See? That +1 indicates the charge of a protonated amine. If we rotate around, we're going to try and find the molecule that it's nearest to. So it is really hairy and kind of challenging to do. But if we do this right, we can sort of get there, get that +1. What we're going to do next is grab the selection tool, find an atom that's near that +1. So we'll go ahead and click this one, then double click on it. Yeah, that just highlighted this molecule here, which indeed indicates that it is a separate molecule from all of the peripheral stuff out here, which is all part of the enzyme. That is the molecule of Tamiflu. I now want you to go up to View and select Show Only. That will let us just see the Tamiflu itself. If we want to get a closer view, we can click this black box, which will make it zoom in and fit the screen. I now want you to deselect and look a little bit more carefully at this molecule itself. As you rotate it around, you should note that all of the bonds here that are in red indicate bonds to an oxygen. So this is an oxygen atom. These are oxygen atoms in resonance with each other. This is a carboxylate group. This is an oxygen atom here that's doubly bonded to this carbon atom. So yes, carbon atoms are shown in gray, and hydrogen atoms and their bonds to carbon atoms and other atoms are shown in white. One thing that should interest you about making medicines in general is that in order to have the medicine be able to actually interact with an enzyme, it has to have sufficient polarity and non-polarity. If the medicine is too polar, that is too water-soluble, it'll just go through a patient and go out with the urine and feces. If, however, it's too non-polar, it won't be able to actually interact with the enzymes and be able to embed itself in active tissues. Thus, you have to find an ideal balance between the polar and the non-polar. As it turns out, this section up here of the molecule, which has 1, 2, 3, 4, 5 carbon atoms with, of course, hydrogens around the periphery, is known as an isopentyl group. This isopentyl group was installed on the initially tested molecule, which just had an oxygen with some other group attached to it instead, and was determined to be much more active than the initial molecule in vivo, that is, inside living tissues. Now, just so you know, the company that did this, a pharmaceutical company in the San Francisco Bay Area known as Gilead Sciences, hired Utah State University's antiviral labs to test this latest analog that was determined to be very active and is now marketed as Tamiflu. Let's go back here to View and click Show All. We now have Tamiflu sitting in the midst of the entire enzyme. We can click this black box to zoom back out and fit everything to the screen. I'd now like you to click Edit and then Select. Down here where it says Group, I want you to click the drop-down arrow and choose Active Site 8A. We'll now choose Select and then hit Close. What this does is it selects our Tamiflu molecule and all of the surrounding enzyme active site up to 8 angstroms from it in all three-dimensional directions. Because the perimeter outside of that doesn't really engage in any significant conformational changes when the Tamiflu docks at the active site, we can more or less ignore that perimeter in order to simplify the model and thereby decrease the number of calculations and the time that the calculations require for this computer model to find an energy minimum. I'd now like you to hit copy open a new window or new canvas, and then hit paste. We've now pasted all of this exciting stuff, including our medicine right here. We'll now deselect it by clicking out here in the canvas. Let's go ahead and zoom in by clicking the black box fit to screen. Okay, now I'm going to turn to some PowerPoint slides to quickly remind you of a couple of important concepts. Alright, so you may or may not remember this from general chemistry, but for any generic reaction like this one, in which reactants A and B are in equilibrium with product C, you can calculate the total change in energy for this reaction by using this equation. The delta E for the reaction, the change in energy that is equal to the energy level of the products minus the sum of the energy levels of the individual reactants. Okay, this is a slightly simplified equation, but generically this is sort of how it is. So for this particular reaction right here, which is once again a little bit generic, delta E for the reaction is equal to the energy level for C minus the sum of the energy levels of A and B. Got it? Alright, so let's apply this to an enzyme-substrate interaction for which the chemical equation is this. Enzyme and substrate individually are in equilibrium with the enzyme and substrate complex or stuck together. That's exactly what we're talking about with the Tamiflu neuraminidase complex. We've got Tamiflu, which is the substrate. It's actually the inhibitor of the enzyme, and then the enzyme itself. When they actually combine, they form the enzyme-substrate complex. So for this situation, the change in energy, or delta E, is going to be equal to the energy level of the enzyme-substrate complex minus the energy level of the enzyme plus the energy level of the substrate. In other words, I've got the energy level of the product minus the energy level of the reactants. This is what we're going to be calculating in a slightly simplified manner in the rest of the video, and then we'll correlate it with actual experimental data. With that said, let's take a look here at our Tamiflu substrate that I've selected right there, as well as the immediately surrounding region of the active site of the enzyme. As I just mentioned, we need to calculate the delta E for the overall interaction between Tamiflu and the enzyme. The way we do that, of course, is by first calculating the energy level of the enzyme-substrate complex, that is, the interaction between Tamiflu and the enzyme itself, and then the individual energy levels of just the Tamiflu and just the enzyme. We then throw it into the equation that I just showed you to be able to calculate the overall delta E. You might ask, what is the purpose of all of this? Well, what we're trying to do here is to determine what delta E is. I will then, in a later video, show you how to change the structure of Tamiflu to be slightly different and then calculate a new delta E. The objective of this lab is to be able to design a new molecule that has a more negative delta E than the original Tamiflu and is therefore a potentially better medicine than the original Tamiflu itself. Hopefully that makes sense. Anyway, this kind of thing is actually done by pharmaceutical companies all the time. So to begin, what we're going to do is select the inhibitor, as I've done here, and minimize it so that it can attain a lowest energy, most stable configuration. We'll go up here to Modify, Drying Minimize, and select 1000 iterations. We'll check all three boxes, and we can probably make this be every 100 steps. We'll then select OK and let it minimize. The inhibitor minimization is now done. Now what we're going to do is determine the overall energy level of the enzyme-substrate complex. To do that, we first have to tell the computer that the inhibitor, selected here, and the enzyme active site are indeed separate molecules and should be treated separately. To do that, we'll once again have our inhibitor right here selected, as I've shown. We'll then cut it out like this and then paste it back in. That once again tells the computer that they are indeed separate molecules and should be minimized independently. I now want you to deselect everything by clicking out here in the canvas. We now go to Modify and Drying Minimize. At this point, we'll now select 0 minimizations and we'll check all three boxes. The most important box right here you should pay attention to is this one that says Include Intermolecular Forces. This box will, of course, include all beneficial or detrimental intermolecular forces between the inhibitor and the complex itself. With this box checked, it gives us the energy level of the enzyme-substrate complex. If this box were not checked, then it would give us the independent energy levels of the enzyme and the substrate separately. We'll go ahead and click OK. The minimization is now done. Now let's take a look at the energy levels. We go up here to Window and select New Data Table. Now if we go down here and click the Molecule tab, you'll notice that we have this column right here that says final Drying energy level. You'll notice that one of these numbers is 496.86 and the other is 18.25. One of those corresponds to the minimized energy level of the enzyme and the other to the minimized energy level of the inhibitor Tamiflu. The units for both of these, by the way, are in kilocalories or kcals per mole. Which number do you think corresponds to which one? Yeah, if you guessed that the 496 corresponds to the enzyme because it's way bigger of a molecule, you guessed right. This 18.25, of course, corresponds to the energy level of the Tamiflu itself. We, of course, want to obtain the overall energy level for the enzyme-substrate complex. How do we do that? Well, we do that by adding these two numbers together. So 496.86 plus 18.25. That number, of course, comes to 515.11. That is the energy level for the enzyme-substrate complex. Now we want to obtain the energy level for the enzyme by itself and the substrate by itself. We'll go back to our original window by clicking up here and going to molecule 2:1. Now we'll go to modify, Drying minimize, but we will uncheck this box. Now the energy minimization will not include any interaction between the Tamiflu substrate and the enzyme active site, so that the new energy levels that it gives us are the independent energy levels of each of those respective substances. We now click OK. Now, in order to see these numbers, we'll click Window and go to New Data Table. We reach down here and click the Molecule tab and look at these two numbers. You'll notice that we have 527.84 as the energy level for the enzyme and 40.36 as the energy level for the substrate. Using the equation that I just showed you, in which delta E for the overall interaction is equal to the energy level of the enzyme substrate complex minus the sum of the combined energy levels of the substrate and the enzyme itself, we end up getting this equation. 515.11 minus the sum of 527.84 plus 40.36. That final number comes to roughly negative 53.1, which is the overall delta E for this interaction. That's the end of this video. Please stay tuned to the next one, in which I'll show you how to modify your overall molecule and determine the new delta E for your new modified inhibitor. Until next time, my wonderful students, have an enjoyable rest of your day.